The adoption of connected vehicle and automated vehicle technology is anticipated at various levels of development and deployment over the next decade. The connected vehicle technology enables vehicles to talk to each other and to the infrastructure wirelessly, providing a 360-degree situational awareness. The automated vehicle technology aims to replace driving tasks that usually require human inputs. This could be things such as throttle and steering control. One primary challenge with this new technology is there are many unknown components and a lack of field data to support engineering design, analysis, and implementation. We often use a traffic simulation to tackle these issues, but there is no one-size-fits-all solution so far for a robust and reliable evaluation of their performance, given the dynamics of components such as wireless communications, control algorithms, and human behaviors and responses to these technologies. Microscopic traffic simulation models rely on algorithms for microscopic driver behaviors, such as car following and lane-changing models. These default algorithms are sufficient for traditional traffic engineering applications, but they are not always well-suited for connected vehicle applications, where the drivers can behave differently or are replaced by machine on certain tasks. This study identifies methods to capture driver responses and behavioral changes needed for the realistic modeling of connected vehicle applications in a traffic simulation. We specifically use vSim application as a primary tool in this study. It is one of the industry standard simulation packages in North America. It has many advanced and customized features for us to explore various solutions to model driver behaviors properly. In summary, we developed a framework for incorporating driver behavior adjustment into the simulation, and then we conducted a case study using an application known as Cooperative Adaptive Cruise Control to demonstrate how this can be done. First, many new applications using connected and automated vehicle technologies are coming out in the near future. We need to have a better grasp not only on how these applications will perform in various traffic conditions and environment, but also under what conditions that they will work best or not work at all, so we can better prepare our infrastructure to support these technologies. That also means a wiser allocation of our tax dollars. Traffic simulation is ideal and the most cost-effective tool for us to understand how these technologies will work or not work, and driver responses to these applications will need to be properly accounted for in the simulation model. This research provides an important guidance on how to model the driver behaviors within this environment and show how it can be done using a case study of a real application. We started by first looking at how drivers behave in response to various technologies. Then, for modeling purposes, we classify the type of changes needed into 3 levels depending on the complexity of the changes. At the simplest level, let us consider forward collision warning as an example. It means the model will need a simple tweak, such as reduced driving speed or acceleration in response to the warnings. At the other extreme, let us take a case of cooperative adaptive cruise control. This is the case where the vehicle is aware of the status of the lead vehicle using wireless communication and automatically adjusts the throttle to maintain a constant gap between itself and the lead car. The throttle control task is now taken over by the machine, and that will require a complete replacement of the driver model in the simulation. We conducted a simulation using this cooperative adaptive cruise control as our case study. Our simulation study shows that this type of modeling can be done with the simulation tool available today, but it requires many customized pieces of software instead of the standard features offered by the simulation package. Specifically for the CACC application, we found that there is a potential benefit in terms of increased throughput, reduced traffic disturbance, which means improved safety, and decreased fuel consumption, even at a low to moderate market penetration of this connected vehicle at 10% to 30%. The benefits are even more pronounced if the platooning operation is restricted to only a specific lane, because it increases the opportunity for platoon formation and helps with the platoon maintenance. Wireless communication quality was also found to have a significant impact on platooning operation. This study provides an approach to properly capture driver behaviors in a connected vehicle environment in a simulation, which means we can achieve more realistic impacts of these emerging applications using the tools we have today. With better understanding of their impacts, we can better prepare our travelers, our vehicles, and our infrastructure in anticipation of the necessary changes and therefore increase overall safety, mobility, and environmental quality of our transportation system.